Welcome to section 6.4, where we're going to be looking at some additional properties of linear transformations. So we're going to come right out of the gate here defining a few different special types of transformations that we can encounter. We're going to look at some of the implications of that, some examples, and do also a little bit of a proof today. So if the kernel of t equals v, so v is the input vector space. So if the kernel of t, which is everything in v that transforms to 0, if everything that transforms to 0 in v is all of v, then that means that t, everything in v, transforms to 0. That means t is what we call the zero transformation. And that can be visualized right here. So again, if everything in v all transforms to only 0 in w, so that means the kernel is all of v, that is called the zero transformation. This one is more of kind of a special case. We're not going to be working with it as much as these other two. For this next one, if the kernel of t is the 0 vector in v, so in other words, if the only thing that transforms to 0 is 0, okay, so if the 0 vector in v is the only thing that transforms to the 0 vector in w, then t is what we call 1-to-1. And you'll often see my shorthand for this is just like 1-1, 1-to-1. So a transformation is 1-to-1 if the 0 vector in v is the only thing that transforms to the 0 vector in w. All right, and the concept of 1-to-1 has more implications behind it algebraically, but essentially the kernel is the kind of the litmus test. The kernel indicates to us if that 1-to-1 relationship exists, by having us look only at the 0 vectors. Okay, so 0 vector in v transforms to 0 vector in w, and it's the only thing that does, then the transformation is 1-to-1. If the range of t is w, so if the range is all of w, we call t onto. So a transformation is onto if, so you take the basis for v, you transform all of those, and then you span that. If the span of all of those covers all of w, not just a part of it, but if it covers the whole thing, then the transformation is called onto. Okay, so these two are really the big ones that we're going to be talking about a lot. So a transformation is 1-to-1 if the kernel is just the 0 vector, and the transformation is called onto if the range is all of w. So let's take a look at an example. So we're transforming p2 to m2 given a transformation of a polynomial of degree 2 or less, p of x equals the 2x2 matrix of p of 0, p of 1, p of 2, and 0. Is t 1-to-1 onto both or neither? So we need to look at the kernel. So the kernel of the transformation. This is all the inputs. So that's going to be, so like ax squared plus bx plus c, such that if we transform that polynomial, we should get the 0 matrix, right? The 2x2 0 matrix. So if a polynomial transforms into that, it is an element of the kernel. So in order for something to be an element of the kernel, all of these are going to have to be 0. Right? So p of 0, p of 1, and p of 2 are all going to have to be 0. So what that means, so for p of 0, what is p of 0? Well, if x is 0, then all we're left with is just c equals 0. And for p of 1, if x is 1, that's a plus b plus c equals 0. And p of 2, if x is 2, we get 4a plus 2b plus c equals 0. So if these are true, okay, so whatever values of a, b, and c make this true, those will give us the polynomials that are in the kernel that transform to 0. Now these conditions here, these equations, if you set them up like in a matrix, you'll find that c gives us 0, and so then these equations, you get a plus b is 0, and 4a plus 2b is 0, and the only numbers that satisfy that relationship are 0. So these equations result in a, b, and c all being equal to 0. So what does this tell us? The only polynomial that transforms into the 0 matrix is one where a, b, and c are 0. So 0, 0, and 0. The only one that works for is 0. So the kernel of t is just 0. All right, that's the only result that produces this matrix when transformed. So the kernel is just 0. The only thing that transforms to 0 is 0. So t is 1 to 1. Now the next question, what about the range? So because we know that it is 1 to 1, but it could still be both, so we need to figure out whether it's onto or not. So we need to look at the range of the transformation. So the range of t, that's going to be the span of the standard basis for P2 transformed. So that's 1 x and x squared. So again, that's the basis for P2, and transform each of the elements of that basis. So if we perform the transformations, so if the polynomial is 1, p of 0 is still 1, p of 1 is still 1, p of 2 is still 1. So we get 1, 1, 1, 0. When it's t of x, so we're transforming the function x through here. Plug in 0, 0. Plug in 1, 1. Plug in 2, 2. So 0, 0, 1, 2, 0. And for x squared, if we run that through the transformation, we get 0 squared is 0, 1 squared is 1, 2 squared is 4. So 0, 1, 4, 0. So if we look at our range, it is the span of these three matrices. The problem is that the vector space that we're supposed to be spanning and covering entirely, if it's on 2, is M2, which has a dimension of 4. So this contains only 3 vectors, but the dimension of W is 4. So T is not on 2. So it asks, is it 1 to 1, on 2, both, or neither? we can say, therefore, T is 1-to-1 only. All right, so we see that this one is 1-to-1, but not on 2. Now, the next question that we're going to talk about is, how does the dimension of these vector spaces impact this potential result? How does their comparison to each other change or affect the possibilities of a transformation being 1-to-1 onto both or neither? So down here, we're going to have our 3 different cases. So, and I've got some diagrams here for each of them that we're going to fill in. So if the dimension of V is less than the dimension of W, so the input vector space is smaller than the output vector space, then if we transform the basis into W, the problem we run into is that this vector space was too small, and it's not going to cover all of W. It's only going to cover a portion of it. So this means that T cannot be onto. So if dimension of V is less than dimension of W, T cannot be onto, because again, you're looking at the span of the transformed basis. So when you transform the basis and then span it, you're able to cover still a portion of W, but not the whole thing, because there just wasn't enough there to cover all of W. So cannot be onto. If the dimension of V is greater than the dimension of W, so like over here, then if we're looking at the 0 vector in W, right, the 0 vector might go there. However, there's so many extra vectors in here that you're going to start getting double ups and maybe triple ups and like et cetera, et cetera. The 0 vector will not be the only thing transforming to 0. So if the dimension of V is greater than the dimension of W, T cannot be 1-to-1. So, and again, because you're going to get a lot of this doubling up on multiple inputs having the same output, more than one thing transforming to the 0 vector. So it's too much going into too little. So you're going to start having to double up. So cannot be 1-to-1 if V is larger than W is, if they are the same size. So like this, you have the potential for it to be 1-to-1, right? Because they're the right size to do that. And you have the potential for it to be onto, because there are enough vectors here to cover all the vectors here in the span. That doesn't guarantee that it will work, right? Because you still have to check, you still have to test and see if they will work. But if they are the same size, if the dimension of V equals the dimension of W, T is either both 1-to-1 and onto, or it's neither. So if the dimensions are equal, it's either both or it's neither. In the event where we have a transformation that is both 1-to-1 and onto, this gets a special name. This type of transformation where it's 1-to-1 and onto is called an isomorphism. Or in other words, we say that the vector spaces are isomorphic to each other with this notation. Looks kind of like a congruent equation. So, but these are isomorphic vector spaces, this forms an isomorphism. So a couple examples, just kind of standard examples here. So like vector space P2 is isomorphic to R3 via this transformation. Okay. And again, we're not saying that two vector spaces will always be isomorphic to each other or form an isomorphism. The transformation T is what's determining that. So with this relationship, okay, where we transform ax squared plus bx plus c from a two-dimensional polynomial into a three-component vector in A, B, and C. Using this transformation, then this is an isomorphism. So P2 would be isomorphic to R3. It would be 1-to-1, and it would be onto. Same thing, P3 going to M2. So a three-dimensional polynomial or less transformed into a 2x2 matrix with real inputs. Again, with the A, B, C, and D right here, this does also form an isomorphism. And we can verify by showing that it is 1-to-1 and onto. Now, we're going to do a little bit of a proof here. And I filled in some of it already, but we'll be talking about it as we're going through it here. If we have a transformation from V to W, if this transformation is linear, and V1 through Vn, this set of vectors is a basis for V, and T is 1-to-1. Prove that this set of the transformed basis vectors is a basis for the range of T. Okay, so again, if we have a linear transformation, V1 through Vn form a basis. The transformed basis will form a basis for the range if T is 1-to-1. Okay, so we're going to prove that. Now, in terms of showing that something is a basis, we need to show that it spans, and we need to show that the vectors are Li. So the span part is easy, and that's most of what I have written up here already. So we already know that the range, by definition, is the span of the transformed basis. Right? That's just how we define the range. So the transformed basis definitely spans the range because the range is the span of those vectors. So span is no problem. So this set of vectors does span the range. The question is, are they Li? And this takes a little bit more work on our part. So assume that this linear combination is equal to 0. So C1, T of V1 plus C2, T of V2, etc., etc. So we set up a linear combination, set it equal to 0, and if the only unique solution that solves this equation is that the constants have to be 0, that means the vectors are Li. That means that none of them can be written as a linear combination of the others. Okay, so throwing it back to some of our Chapter 4 work. So let's see if we can prove that C1 through Cn all have to be equal to 0. All right, so from assumption, the transformation of C1v1 plus C2v2, etc., all the way up through CnVn, that must be equal to 0. So if this sum is getting transformed to 0, and it's getting transformed to 0 because, again, we know that these vectors, V1 through Vn, form a basis for V, which means they are Li. Okay, so they transform into 0. So C1, V1, C2, V2, etc. That sum, whatever this result is, because it transforms to 0, that means that it is an element of the kernel. But the kernel, in this case, can only be the 0 vector in V because we're assuming that t is 1 to 1. Okay. All right, so what does that mean? That means C1V1 plus C2V2 all the way up through CNVN. If they're in the kernel, and the only thing that can be in the kernel is the 0 vector, then this has to be the 0 vector. All right. So since this set of vectors, like we were saying earlier, since this set of vectors is a basis, it is Li. Since it's Li, that means that these constants, C1 through Cn, must be equal to 0. But now, we were trying to prove that C1 through Cn is 0. So now let's just verify really quickly that this is still the same C1 through Cn that we were looking at. Okay, so we started with this assumption, right? Assume that this linear combination equals 0. Because we know that this is a linear transformation, that allows us to move the constants in, and that allows us to combine across the addition. And that's what gives us this part here, right? So the C1 through Cn have moved inside of the transformation, and now we have the transformation of this sum, which meant that this sum is in the kernel, which meant that that sum is equal to 0. So this C1 through Cn is exactly the same C1 through Cn that we had back up here in the problem. And we just showed, because this set was Li, that C1 through Cn must be 0, which is exactly what we were trying to prove. So our set T of V1, T of V2, etc. up through T of Vn is Li. Since the set spans the range, and the set is Li, we can say, therefore, this set of vectors, T of V1 through T of Vn, is a basis for the range of T. So again, a lot going on in this proof, but again, we used our assumption and the fact that it's linear to get to here. And then we used our knowledge of 1 to 1 to set the kernel equal to 0. So that gave us this relationship here. And we used the fact that V1 through Vn formed a basis to give us this condition that we used to show Li. And because it spans and it's Li, it is a basis by definition for the range. So next up, we're revisiting the matrix transformation. So the matrix transformation, recall, goes from Rn to Rm, Okay, via this matrix multiplication, A times X. Consider the special case when the two vector spaces are the same size. So when M equals N. So we're going from our N to our N. Okay, so we're going to have the same dimension for both of these. And the matrix is going to be a square matrix, an N by N matrix. Because the dimensions are the same size, this tells us it's either both 1-to-1 and onto, or neither. But now if we relate back what we already know about the matrix transformation, we know that the dimension of the kernel plus the dimension of the range is equal to n, right? That's the dimension of V. But in this case, that's also the dimension of the matrix, right? N by n. So if the kernel is 0 and the range is n, okay, or I should say the dimension of the range is n, this becomes 0 plus n equals n, and t is both. Okay, because the kernel would have the 0 vectors, so that's nothing. And then the range would cover all of the output vector space. So that would be a dimension of n, right? And that's how we define 1-to-1 and onto. 1-to-1 means the kernel has only the 0 vector in it. And onto means that the range covers all of the output vector space, which in this case has a dimension of n. So if this is 0 plus n equals n, then t is both. But if it's any other combination, if the kernel has something else in it that increases its dimension and the range drops in dimension, then that would be neither. So along similar lines, suppose that the dimension of the kernel is 0. In the matrix transformation, remember the kernel represents the null space of A. So if the kernel is 0, that means that the null space would be 0. And if we have a matrix whose null space is 0, okay, so the only solution set to that homogeneous system of equations, if the only solution set is 0, that means A is invertible. Okay, this is one of our equivalencies in the invertible matrix theorem. The conclusion we can draw from this is that if our matrix transformation is an isomorphism, this will be an isomorphism if and only if A is invertible. Okay, all of these conditions lead us to the idea that the matrix transformation being an isomorphism, so being both 1-to-1 and onto, will occur only if A is invertible, and vice versa. A will only be invertible if the matrix transformation for A is an isomorphism. This is really nice, particularly because when we're dealing with square matrices, we have a nice quick check to determine invertibility, and that's the determinant. So, like for example, for this matrix transformation, we have 1, 2, 2, 4 times x. If we take a look at the determinant of that, that is 4 minus 4, which is 0. So the matrix is not invertible. And if the matrix is not invertible, that means that this transformation is not an isomorphism. So thus, T is not an isomorphism. Now, in general, when we're talking about isomorphisms, the only condition to be an isomorphism is that it's both. So just because it's not an isomorphism doesn't mean it's neither automatically, like in general. In general, it could still be 1-to-1 or onto, just not both. But in the case of the matrix transformation, because of this relationship here, and we're looking at the dimension of the kernel and the range and all of that kind of stuff, in this case, it would be a both or neither situation. So therefore, T is neither one-to-one nor onto, given the conditions for the matrix transformation. So again, in general, something not being an isomorphism doesn't automatically imply that it's neither, but if we look at the dimensions of these two, right, we have the dimension is n, dimension is n. So in this case, because these are the same, it is going to be either both or neither. And that gives us, it's not both, so it has to be neither. Okay, so this is the kind of situation where we could make that neither claim, as long as the dimension of the input vector space and the output vector space are the same. And that brings us to the end of section 6.4 and to the end of chapter 6.